Welcome to the Neuromodulation podcast, presented to you by the International Neuromodulation Society. Dive into the forefront of today's emerging neuromodulation techniques, insights, and ethical and clinical applications. Subscribe now to join the multidisciplinary collaboration of medical care providers, scientists, and engineers who are part of the global conversation that's shaping the future of healthcare. Welcome to the Biostatistics Article's live reading series, presented by the International Neuromodulation Society and developed in collaboration with the Newcastle Cognition Lab at the University of Newcastle. I'm your host, Mandy Soleil, and it's a pleasure to have you here. We're pleased to offer this ongoing series of short articles explaining how to critically apprise clinically relevant literature to evaluate evidence and inform practice. The entire series of articles is available on our website at www.neuromodulation.com/biostatistics-articles, and a direct link to this article is available in the episode show notes. We've translated each article to a live episode on the Neuromodulation podcast to bring versatility and ease to your statistics learning journey. Each primer features a single topic and an example within the context of clinical neuromodulation research and practice. Upon reading and/or listening to these articles, learners will be able to understand statistical methods, their interpretation and their limitations, identify cognitive biases to avoid inadvertently misinterpreting evidence, and interpret data for a deeper understanding of clinical research to inform clinical practice. And now, I present to you Professor Konstantin Slavin, head of the Stereotactic and Functional Neurosurgery section at the University of Illinois Chicago, or UIC, and president-elect of the INS. His term as president begins September 1st, 2024. Thank you for tuning in.
This is the next installment in the Biostatistics Articles for International Neuromodulation Society. What a p-value can and cannot tell you. Written by Garston Liang, Quentin Gronau, and Alexander Thorpe. The p-value can tell you the probability that a null hypothesis generated data. The p-value cannot tell you the effect size, the quality of the alternative hypothesis, that there is no effect, the sampling plan, or details about data pre-processing. Part 1. For the love of p-values. Love stories stand the test of time. Romeo and Juliet, Paris of Troy and Helen of Sparta, Emperor Hadrian and Antinous. Surely there are but a drop in the vast of ancient ocean. Each story contains their own crescendo, tragedy, and pathos, and the dynamics are as enthralling as the relationships are complex. So where is this vastness might we find the science's love affair with the p-value? The humble p-value is a familiar traveling companion. Long is the road of scientific inquiry, and so familiarity fosters the comforts of convention. Yet, the p-value is often misunderstood, despite, or perhaps because of, its constant companionship with the measurement, consumption, and interpretation of scientific writing. Here we revisit an old friend. In this primer, we explore what a p-value is, what p-value tells us, and what a p-value cannot. However, together we hope to lift the rose-colored spectacles of convention and to look honestly upon the p-value for what it truly is. The figure illustrating this part has a person discussing the alternative hypothesis when his bus may be only late on Tuesday and Fridays, but maybe 10 minutes late, having multiple hypotheses presented in his mind. So the null hypothesis has a p-value, and the bus problem is the source of the contention. Part 2. What does p-value tell us? The p-values help us draw statistical conclusions about the state of the world by highlighting the probability, or more often, improbability of a single baseline hypothesis. Formally, the p-value is the probability of obtaining the data or more extreme data, assuming that the null hypothesis is true. To make the abstract more concrete, consider the bus dilemma in a diagram. Having recently moved, I want to know whether my local bus leaves on time. Most days it is late, and other days it is on time. Besides the emotional frustration, I want statistical verification of the local bus company's claim that their buses run on schedule. Suppose each day for a month, I time the bus past the scheduled arrival time, being in the middle of the diagram. From this data, we can calculate a variety of summary values, such as average waiting time. For demonstration purposes, let's suppose the average waiting time is 20 minutes. Before acquiring the data, however, we might have assumed that the average wait time should be 0 minutes, at least according to the bus company's claim. This baseline assumption is also known as a null hypothesis, signified as H0. Shown on the right side of the diagram, the null hypothesis is a hypothetical and, at a minimum, possible state of the world. It serves as a baseline and generally represents a state of ignorance before any data is observed. Once a null hypothesis is proposed, the p-value is a statistic that quantifies how probable or conversely how extreme our dataset would be if the null hypothesis generated our data. In the example, the p-value would present how likely was it to obtain mean wait time of 20 minutes if the bus runs on schedule. A low p-value means that these data were unlikely given the null hypothesis was true, and so the real world must be quite different from the hypothetical null world. In other words, we reject the null as a viable state of the world. Statistically, we would conclude that the bus does not run on time with p-value less than 0.05 and propose new alternative hypothesis about the bus's actual schedule, shown above the clouds in the diagram. Part 3. What a p-value cannot tell you. The p-value cannot tell you about whether the null hypothesis was a good baseline. Null hypothesis cannot be derived from many different sources, ranging from expected outcomes from chance, like when the coin tosses should converge to 50% heads, to inform specific values based on previous observations, meaning that my next-door neighbor says the buses are 2 hours late. Similarly, the p-value cannot tell you about the quality of the alternative hypothesis. The logic of the above process, called null hypothesis significance testing, is such that alternative explanations are proposed only after the null hypothesis is rejected. However, the p-value does not make contact with a new explanation and so cannot tell you whether the new hypothesis offers a better account of the data. Along a similar vein, a p-value cannot tell you that there is no difference in the data. If the null hypothesis is retained, there is no evidence that the null is true, only that the data could have been generated from the null hypothesis. Note, for a Bayesian framework that does account for both alternative hypothesis and evidence for the null, see the Bayes factor primer by Gronau et al. In this series. A p-value can be calculated for any hypothesis, but assessing the quality of the null and alternative hypothesis is a task for the reader. Part 3.1. P-value is not an effect size. The p-value is not a measure of effect size. The fact that an effect is statistically significant can be divorced from what makes an effect clinically important. In the bus example, I could have collected a large sample of data, meaning recording every day of the year, and statistically determined that the bus was late every day by 1 minute. Although this effect would be statistically different from the 0-minute null hypothesis, who would care? In some scenarios, small effects may be important, whereas in others, only large effects are worthwhile pursuing. Clinical judgment of the effect size is therefore highly informative alongside but distinct from the p-value. Part 3.2. P-value cannot tell you about the sampling plan. Before the p-values are calculated, experimenters must decide on how to obtain data from their population. Many decisions are made at this point, such as the ideal sample size which affects statistical power, or whether to stop data collection based on time, meaning next 3 months, or until a minimum number of subjects are obtained, meaning at least 20 patients. Although these decisions are made prior to the analysis, they affect the sampling distribution of the data, and consequently, the p-value. Interrogating the methodological details would be prudent. Part 3.3. P-value cannot tell you about data processing. At the data level, the p-value is silent with respect to how the data were processed. Once in custody, A dataset can be interrogated and shaped through transformations, median splits, or outlier removals, to name just a few techniques. While each of these steps may well be necessary for data analysis, it is important that the reader is able to assess the complete chain of events, because p-value bears no trace of the original data prior to processing. Further reading. Below there are 3 resources that discuss issues around p-values in greater detail. These include paper on effects of sizes in greater detail and why the p-value is not enough, written by Sullivan and Fine, and published in Journal of Graduate Medical Education in 2012. The problem with interpreting effects is strictly by significance, with value less than 0.05. The p-value fallacy and how to avoid it. It is published in Canadian Journal of Experimental Psychology. And finally, common problems with p-values and Bayesian alternative approach, written by Wagenmakers in 2007 and published in Psychonomic Bulletin and Review. Thank you.